Hi everyone. Welcome to the class. I hope the exam went well. What is going to happen in the class for the last 3 lectures is that we are going to look at some advanced topics in, let's say, graph representation learning, and we are going to do a series of guest lectures. And I'm going to talk about today's guest lecture next. So the lecture today will be about geometric graph learning or geometric deep learning. And kind of the core concept of today's lecture will be being able to develop models that are invariant to symmetry. So kind of that account for symmetries in the data and are, because of this, able to learn better with less data, more efficiently, and so on. The applications that we are going to talk today about is chemistry. Is basically how do we capture structure of molecules using machine learning. And the lecture will be given by Minkai. He's a PhD student here in the computer science department at Stanford, and actually one of the leaders in this area of using geometric deep learning, diffusion models, things like that for molecular applications. So I'll hand it off to Minkai now.
Thank you, Jure, thanks to Jure for having me today here to introduce both this promising direction in the advanced graph representation learning, and also I can incorporate our most recent progress about graph generation or geometry generation using diffusion models. Okay, I think Jure has nicely introduced me. So I'm a PhD student at Stanford at computer science, working mainly on intersection of generative model and graph representation learning. So the application will mainly about graph generative models on molecular structure, on drug discovery, on protein design, something like this. Okay, so this will be the outline of today's lecture. So first, I will introduce what is, when we talk about a geometric graph, what we are talking about, what it is, and what is the key difficulty of developing machine learning models for geometric graphs, significantly different to your previous content for typical graph learning. And the second part is, okay, now we know what is geometric graph. We know what is the difficulty of learning on geometric graph. Then how we develop an effective model for a geometric graph. So we introduced some mainly 2 classes of graph neural network for geometric graph. And the last part is, considering we have already defined data, we have already developed some modern architecture like a graph neural network, how to use this graph neural network to tackle real-world challenges. And I will introduce our most recent progress of geometric diffusion model, which is capable to generate a very, very realistic molecular structure. Okay, so first part will be geometric graph, and maybe we can have a very brief recap of a very typical graph. So what is graph? I think you have learned it for the whole quarter. It's adjacency matrix and also a collection of nodes. The node have node feature, and they are defined by some connection of the adjacency matrix. And occasionally, in the adjacency matrix, the AIG also can contain some edge feature, so we want to learn over such graph. Yeah, very typical thing. And I think, these 2 equations, you also have learned it for many times. So how to do learning on graph structure, we actually use the graph neural network, and it is mainly composed of 2 steps. So one step is aggregation. Currently we are on one node and we have multiple neighbors. The neighbor will generate or predict, or we want to learn some message from the from the neighborhood, and the neighborhood will pass their message toward you. You will learn aggregation function to aggregate the information, and after you aggregated the information, you will also have an update function to learn how to update current node embedding. So multiple perspective of understanding the traditional graph neural network. So these are two most I think well-known or accepted perspective to understand the graph neural network. One direction is just look at one layer and you see, oh, it is one node and there is neighbor. You repeatedly pass the message and aggregate the message and update node embedding. And I think the computational tree has also been incorporated in the lecture. So when we're considering multiple graph neural network, you can see in current layer, you aggregate the information from your neighbor. And if you look at the before layer, you can see your neighborhood's embedding. They actually aggregate the information of their neighborhood. So by stacking multiple graph neural network, actually you just exponentially expand your perceptual field and learn more and more feature from the neighborhood, something like this. Okay, and before I introduce what is graph, what is geometric graph, I need to also make a brief recap of the graph level prediction task. I know for graph representation learning, I think we usually concentrate on three kind of tasks. One kind is node level prediction. We want to predict some feature of a node. And another similar application may be edge prediction. So predict some feature on the edge. And but today maybe we first consider the problem on graph level prediction. So this is very useful especially for like a molecular graph, for small graphs. So like we have a molecular graph and we want to predict some feature or property of this molecule. So what we do in addition to the typical message passing neural network, we call it permutation equivariance neural network, but never mind, just a typical graph neural network. Between different layer of graph neural network, we also have some advanced layer like pooling. And yeah, I think I also see the previous syllabus. I think differentiable pooling has been also introduced before. So in addition to like just learn the embedding on node level, we also can use some pooling to pool multiple nodes together as a supernode. So this kind of formulation can significantly reduce the number of nodes during message passing, and also it can help to enable some message passing between multiple group of nodes. Or in other words, it makes more sense for molecules, because in molecules there are like chemical rings or something like this. They are very predefined local structure. So this kind of pooling can learn to pool the local structure towards as represented as some pseudo single node. So enabling some message passing between the local graphs makes the information transformation or message passing more effective, significantly improve many tasks for molecular property prediction. Okay, so by last slide, I just introduce like mention how to learn graph neural network for molecules. Now maybe we can have a look again of when we do graph representation learning for molecule, actually what we have as the input. So this figure is pretty typical, right? So it is, again, so node, different nodes are labeled with like item type, and they are connected by valence bond, and the edge can also be labeled with some chemical type, so something like this. But most importantly, actually, we also in many times have the 3D structure of molecules. And in many real-world applications, we are very interested in this kind of 3D structure of molecules. For example, when we want to model the how a molecule is act in some solvent or in our human body, how a protein, if you have some disease, there is some protein, there is some functional problem of your protein, and you eat a drug, how the drug will solve your problem. Actually, they are all effective in the 3D space. We want to model them in the 3D space. So it is very informative. And another thing is considering for one molecule. Actually, even one molecule will have different 3D structure in different temperature, in different solvent, something like this. And when they are in different conditions, they will have different 3D, and then they have different property. So it never makes sense to, for some property, never makes sense to input just the adjacency matrix graph and make some property prediction, because the property actually is directly related with the 3D structure instead of the 2D structure. So, okay, so now this is the theme of this lecture, how we do representation learning on the 3D structures. And yeah, molecule is the most exciting and promising area of this direction, so geometric graph. I mean, it seems like there will be some killer application of geometric graph neural network. But more broadly, there are also many other scenarios. They are also interested in geometric graph. So in addition to small molecules, there are also a little bit larger molecule like protein, DNA. And these three are organic structure. So for inorganic structure, there are also exciting research on crystal and catalyst. And also, those are in macro world. But in our physical macro world, there are also applications like transportation, the city layout, and vehicle and robotics. So this is really an exciting area. Okay, so now we can formally define what is geometric graph. From your last feedback, I feel like all of you are very familiar with what is graph. So now I can just say, in addition to typical graph, so what's new is just every node is additionally embedded in our Euclidean space. So every node is associated with some 3D coordinates. So more formally, so for this lecture, I will name the traditional node feature, like item type, as a scalar feature. But for the coordinates, I will name it as tensor feature. I think this is some terminology used in like a physics course. So scalar means that they don't have direction. They are just some number or some value. But for tensor, they are in addition to the like in physics, we usually make notation of tensor as arrow. So in addition to the length of the arrow, we also have the direction. So this is the intrinsic difference. It is directional. Okay. Okay. So before I introduce what we are concerned about, like invariant and equivariant, maybe I can provide some very intuitive understanding of why we want to do invariant prediction or equivariant prediction. Okay, so for geometric graph, let me just take a molecular structure as an example. So firstly, maybe let me just introduce the supervised learning task. This slide just show a supervised task of prediction of some property of this structure. Either some functional property of this protein or binding affinity of this protein. So a brief introduction of binding affinity. So when we have some disease, I think the majority of our disease is kind of because there is some protein. There is either some functional protein was disabled or there is some like virus protein in our body. So when we eat a drug, actually, we hope the drug to be like in this figure. Maybe this is our drug. So when we eat a drug, the drug will combine or bind on the protein structure. If the protein is good, maybe we want to like reactivate the function. Or if it is virus protein, maybe our hope is to deactivate it. But anyway, so I just want to see when we eat a drug, the true effectiveness is we hope they can bind together. Okay? But anyway, they are all like a graph level prediction. When we have a 3D structure, we want to have some prediction of the property of this 3D structure. And one interesting thing here is how we represent the 3D structure. So it is the n by 3. So when we have n node, it is n by 3 matrix to represent the coordinates. So every node will have coordinate. So n node have n by 3 matrix to represent the coordinates. But when we do some rotation or translation of this structure, this n by 3 tensor definitely will change. So, but no matter how it changes or how it rotates or how it translates, it is still the identical structure. And we really hope that the prediction should be the same. So this is the high-level idea of what we are concerned about to develop our neural network. So it should capture such symmetry of this physical world. Okay, so this one is for single number prediction. For example, some property. So we just predict a value. Here we also have some other application, like this one, like in computer vision, we usually call this kind of application as dense application. I mean, for example, if we do image classification, we just want to output, which class it is. By analogy, when we want to do like a segmentation of this image, we will output a very dense output of all the pixels to show the segment. So this is kind of similar. I call it a dense output or dense prediction. So for molecular simulation, I think it should be covered in like high school physics, so or university physics. So something like when we can start from a very unstable structure, and molecular simulation means we really want to know what is the stable structure of this molecule. And what we do is we have some method to calculate the electric force between different atoms. And when we have this kind of force, the force can tell us how to move these kind of molecules. And we move again, calculate the force, move the structure, calculate the force, update this structure. And finally, we hope that we can have a very stable structure, which means when we calculate the force again, we hopefully the force is 0 now, finally. So which means we get a stable structure. And here, so very traditional simulator. So it need actually I think they solve something like a Schrodinger equation and calculate the force. So really expensive. And here what we want to do is like a Schrodinger equation to collect many structure and their corresponding force, structure and corresponding force, and we want to use neural network to learn what's the force on current structure. So it is a dense prediction. I mean, the output is also n by 3. So if we have n nodes, we have n by 3 dimension of forces acting on every node, every atom, and move this atom. So here is another interesting symmetry, right? So considering we do this kind of simulation, we can also rotate and translate the input molecular structure. And how should the force move? So it should rotate together, right? So when we rotate an input structure, the force is mainly by like interactions. So the output should rotate together. And considering translation, no matter how we translate, force will stay the same. So this is another symmetry of this kind of task. Okay, and finally is a very brief idea of what we can do in most modern machine learning, especially in the era of AIGC, you know. So every day we can see Stable Diffusion generate some fancy images, and also ChatGPT generate some fancy stories. So there is also this kind of very exciting progress in graphs. So every day we see many pharma company, drug company, they actually seems like want to solve this drug development problem. They want you give like your COVID virus protein, and they can generate some molecule, probably can bind it on the protein, and they can also another promising direction is like they also have some humans antibody on this virus protein, and they can modify the antibody to make it more effective and develop a method to synthesize that antibody. But anyway, just built on the geometric deep learning, develop a new generative model for these geometries. Okay, so here I want to formally like chat about the obstacle or difficulty of this area. So formally we can see when we have a structure. Okay, this structure is here, but we don't know how to construct our coordinate system. We have multiple different ways to construct our coordinate system, and then the coordinates of current geometry will be different. But you know, the atom or the not the atom, the objective or the molecule, no matter in which coordinate system, it should be the same one. Or in other words, if we fix the coordinate system, it can be seen as like we have a molecule structure, and we do multiple like rotation and translation to move it all around in our world. But it is still the same. It should have the same property, something like this. And however, consider how we use traditional graph neural network to process our node feature. A naive way to process the, as I introduced before, for the geometric graph, the only additional feature is the n/3 coordinates. So how to process this information coordinates? A very naive way is just, oh, it is node feature, right? Every node has coordinates. Just concatenate it to node embedding and make it as together as a node embedding and do message passing. The problem seems like it is solved. Is it really solved? Definitely not, right? So we can translate and rotate, and when we translate and rotate, the coordinate will change. And when the coordinate change, after we input into like a traditional graph neural network, every node embedding will change, and the output will change, the prediction will change. This is definitely not what we want. So yeah, this is the problem. Traditional GNN, when they see different like location or orientation of identical geometry, they don't know they are the same. They say, oh, they are different. Okay, so what we want to do is let's try to think about some novel method to make our graph neural network can see, oh, these two geometry, I know they are described differently, but they should be the same. And when we make prediction, the prediction should be the same. Okay, and the before slide is mainly about the input space. So when input space change the symmetry, rotated or translated, we want to make the prediction still the same. But for the output space, there is also some symmetry, which I have mentioned before. Like when we do optimization or simulation of the molecular structure, when we rotate the input, we want to make the predicted force also rotated together. But when we do translation, we hope, the predicted force should stay the same. So there is also symmetry consideration of the output space. So which means, which we use the word equivariant. So input change, output change together. So yeah, this is formally named as equivariance. Okay, so this is the formal definition of equivariance. So firstly, we can abstract our graph neural network as a function. So the function f, we have the input space x and the output space y. So in the example here, so our input space is the molecular structure and the output space is the force. Or more formally, here we are mainly interested in the 3D structure, so maybe you can abstract the problem as input coordinates and output the force. So equivariant means when we have this kind of function, we can apply some transformation of the input space. We name it like rho x. And we similarly want to make some transformation in the output space. We name it rho y. So equivariance formally means for every action in the x space, there is a corresponding action in the y space. They are bijective. So a very natural choice is they should be rotated together and translated. They are not translated together. Okay, just think about rotation first. The rotation is input how rotate. Output should rotate in exactly the same way. So this is the formal introduction of equivariance. Yeah, but yes. So translation is not the case, but still called equivariance. We will present it later. So here is some very intuitive way to have a sense of what is equivariance. So maybe look at this first. We have such a structure and we make false prediction. Okay, we have all the directions. And if we do a roll, so it is some transformation, or in practice it is rotation of this system, and then the forces should rotate in the same way. And here is even more informative way to illustrate the equivariance. When we rotate the structure, the two arrows rotate together, which indicates the force rotate together. Okay, so beyond the equivariance, here we also define what is invariance. Invariance is kind of similar. So we have a function, similar function. Here, input an image and we input, who is this famous guy? Okay, so here, this one, okay, yeah, it's Professor Leskovec, right? And then there is some rotation and translation, but you can still know this is still Professor Leskovec. This is not Minkai, right? And yeah, this is the formal definition of invariance. So still the space X, maybe it is an image, and we do some transformation of the image and then input to the function f, which is some neural network. And we hope that no matter how we apply the rho x, we stay the same prediction. This is invariance. And this is a lecture, so I need to present everything in a rigorous way. So formally, invariance is a special case of equivariance. So look like invariant and equivariant. Actually, invariant is just a special case of the equivariance, which means rho y is defined as like never apply any action. So here means no matter how you rotate or translate your input, the upper space transformation is no transformation. Sorry?
This is the bijectivity, though, that you defined before. You said that equivariant functions have to have a bijective relation between px and py.
Yes. Indeed, I realize I may make some wrong statement of bijective. Yeah. Sorry. But yeah, thank you. You are listening very carefully. Yeah. So the rule here is defined as no transformation. So formally, invariance is a special case of equivariance. But in this lecture, I will just, I don't want to lose the meaning of these two words. So when I mention equivariance, I just always want to see, oh, they change together. And when I mention invariance later, I just want to see there will be no change of output space. Okay. But formally or theoretically, invariance is a special case of equivariance. Okay. Here I just have a brief introduction of all the tasks we will concentrate on later for all the neural network design. So what we talk about today is a special, mathematically, it's a special group in our world. So it is called a special Euclidean group 3, SE3 group. SE3 group means we consider the transformation as a combination of rotation and translation. So a little bit more. So there are also just a typical Euclidean space, E3 space. So in E3 space, the additional action is reflection. So but in molecule, when you reflect a molecule, actually the property will change. So we never consider reflection. We only consider rotation and translation. But anyway, I just want to have an introduction of what transformations we will consider today. And the two main tasks are also actually introduced. So a very classic problem is do energy prediction. So every structure we have a potential energy, so how many potential energy it has. So no matter how you rotate or translate, it should have the same energy. So it is a very typical invariant prediction task. And another task is we want to do a force prediction, and as introduced before, it should be an equivariant prediction task. By the equivariant, actually it means equivariant to rotation, but invariant to translation. Yeah, we want to do this kind of prediction. There is some analogy in image domain. What is invariant and equivariant? So when we do classification, no matter how you change, stay the same. But when we do segmentation, what we output is on every pixel coordinates or every pixel position. So they will also change together, considering rotation and translation. So this is equivariance in the computer vision domain. Okay, a summary of all the data and the symmetry we need to consider. And here is a lot of content, but maybe I can concentrate on a graph to make some analogy on the graph. So graph actually is a permutation symmetry group. So by permutation symmetry, we can also consider two types of prediction, a scalar prediction and a dense prediction. Okay, scalar prediction means we want to do graph level prediction. Then, so we predefine order of this graph, and in PyTorch or TensorFlow, it is stored as a matrix. So different nodes, they are combined together as a matrix. But actually, we can change the order of different nodes. They are arbitrarily stored. And when we do a graph level prediction, no matter what order is the different node, we should do the same prediction. So it means the graph never change with different order of the nodes. So this is permutation invariant when we do graph level prediction. we are also sometimes interested in like prediction for every node. So node level prediction. For node level prediction, when we change the order of the input of different node, the output should change accordingly. So this is called permutation equivariant. So they should change in the same way. So I think this is also the design philosophy of a graph neural network to some perspective. The message passing, when you do message passing, you never consider the order of your neighborhood. So the message passing naturally is permutation invariant. And I think this is also one of the reason of the success of graph neural network. Okay, so now let me introduce the how to do graph neural network for this kind of symmetry or symmetric data. A naive way is, okay, although our typical graph neural network couldn't capture the symmetry, we can do some data augmentation, right? This is also, I think, used a lot in computer vision when they do like classification. They randomly rotate and translate the image and force the model to learn the same prediction. Here we can do the same thing. With a single data, we can just enumerate all the positions and force the model to make the same prediction. But this is very expensive, very time-consuming, and also not very natural and elegant. And here, what we want to do is we should develop a GNN aware of symmetry. Just one data is enough. Here is some intuition. So when you never design the geometric graph neural network, you allow yourself to explore in the whole learnable function space. And finally, your data constrain your model to be some subspace, but still very large. But here, what we want to do is you need to constrain your neural network to make it to be just the invariant functions. And you significantly constrain the function space you explore. And hopefully, you can effectively learn what you want. Okay, so today I will introduce two kind of graph neural network. One type is invariant graph neural network, and another type is equivariant graph neural. Oh, sorry.
You go back to the previous slide. Here, just clarifying, are you using the phrase geometric function to mean the same thing as equivariant function?
Geometric function, equivariant function, not the same. So geometric graph neural network has many different classes. So we will introduce later. So many different graph neural network. And our ideal goal is to develop very effective geometric functions. But currently, we still don't have enough knowledge to fully capture all the geometry information. So later I will introduce more. Okay. Invariant graph neural network and equivariant graph neural network. Okay, so here are mainly two classes of graph neural network. Invariant means we make we only act on some invariant feature, while equivariant neural network act also on some directional feature. I will introduce them more later. Before formally introduce the neural network, I can, actually I think I have introduced all the information before. Like simulation need to, what is molecular simulation? Oh, maybe another knowledge is when we do molecular simulation, I just explain from the force view. Actually, you can also understand it from the energy view. So when we do molecular simulation, we actually want to find the local minimum of the energy surface. So we want to find the structure of the lowest energy. And what we do is using the force to optimize the structure. And the force actually can be viewed as the gradient of energy. So negative gradient. So it drives the structure towards lower and lower energy, and finally we can get the local minimum of the energy function, and it is a stable structure. Okay, yeah, we can use force to optimize the structure. Okay, so let's see the task, how we train this kind of model. We have atom type, and we have their positions, the 3D coordinates. And what we want to learn is we want to predict energy, and we want to predict their force. And the first class model we will introduce today, they just learn how to predict energy. And for force, although it should be equivalent, it can naturally be calculated by, if energy is learned by some neural network, we can just take this neural network, calculate the gradient of the output towards input, and this gradient can be viewed as the force prediction. Okay, now introduce the first class of geometric function, which is invariant graph neural network. This is Shinet, I think, has been like many years, 5 years, yeah. This is the first, I think one of the first graph neural network on 3D structure. So it is also still the message passing framework. So let's see the equation. On the L layer, how we update the node embedding. The node embedding is updated at, maybe just look at this equation. W is some neural network you can understand. And what we do is, when we want to the embedding of this node, we first calculate all the direction from the neighborhood to this node. And this direction is input to the neural network, WL. And W will output some like a controller on this edge, which controls how the information will propagate from this node to this node. Something like this, yeah. Okay, so formally, we have WL as a graph neural network. This graph neural network, the input is the direction from the neighborhood to current node, and the output will be some like a filter acting on the neighborhood's embedding. And finally, all the embedding will be summed together as a message aggregation, simple message aggregation just by sum. And this will be used for updating our current node embedding. Okay, so let me introduce how we can make it invariant. Yeah, actually, this is very similar to our previous graph neural network. So the only difference is we use some edge feature, which is the direction to control the message, and the message just aggregated together. And how they achieve invariance, this neural network do a very simple thing. So, okay, here the input is directional thing, right? From neighbor to this node. Okay, I can do some very simple thing, just make this tensor to a scalar. So what they do is called scalarizing. So actually, when the neural network input is the direction, they first calculate the length of this direction. So they only use in other words, only use the distance information of current bound, and input this bound as the controller of the message passing. Okay, yeah. So from this figure to next figure, we actually do some rotation of the molecule. But no matter how we rotate this molecule, their bound distance stays the same. So considering bound distance stays the same, so look at the equation. This input is invariant distance, and naturally the output of this W is also invariant, and naturally the message passing is invariant, and naturally everything is invariant. So very high level idea is in one word. So no matter how we rotate and translate our current structure, their inter-distance never change. So this kind of graph neural network, the high level idea is just take the distance as the edge feature, so which never change, consider rotation and translation. And yes?
How can this network take into account the angle between the two bounds?
Yes, this is an improved word, so I will introduce later. Yeah, so very simple.
Is this just equivalent to dropping the X matrix entirely and then augmenting the feature matrix with one column? It's just the distance.
You mean give up the coordinates tensor and just augment the edge feature?
Yeah, is it equivalent to what we're doing here?
Exactly the same, actually. Yeah. So very intuitive understanding is so. Yeah. So yeah, I think the idea is most important. So maybe we can skip this kind of details. So for distance, it is just a single value. So they make some method called RBF to expand the distance. It is a single value to higher dimension and make it a more informative edge embedding. But whatever, just some invariant feature depend on the edge embedding, on the distance, sorry. Okay, and this is so defined, I think considering the time, maybe skip this kind of network architecture. Yeah, we can skip it. This is just the message passing framework we have introduced before. So CFK, and what they do is, in addition to message passing, they first do message passing to aggregate the information, and then do some item-wise like updates of the aggregated information and added to the node embedding, something like this. Yeah, seems like should not be very interesting. Okay, and so,
I have a question, but feel free to.
yeah.
So a lot of molecules don't have one stable structure,
Yes.
right? And they might spontaneously isomerize or whatever. And so when you have this representation where you say this is the coordinate of each atom, and then we're going to minimize it, and then that's going to be the final structure,
Yeah.
kind of can be misleading about what actually is going on chemically. And I guess I wondered if there are alternate representations that consider that more explicitly.
I don't understand that.
Like, for example, if you know that a molecule can convert between two different
Yes.
3D structures,
Yes.
can we represent both of them simultaneously rather than just one?
You mean you want to have a representation, but it capture all the information of a different stable
Yeah.
structure? Oh, this would be, I think, kind of difficult. Are you from chemistry department?
I know a little bit, yeah.
I think they are interested in something like, this is why they are interested in some generative model, because generative model can do unbiased sampling of all these structure. And they do some statistics over all the structures. But for only one representation, I think it's kind of difficult. It is always some statistical things in chemistry. So always multiple structure and do some aggregation. Yeah. Okay, yeah. And finally, we can make some prediction on every node and sum them together as an energy prediction. Yeah, very, very intuitive. And this is the training objective. So maybe you can take a look in this model. So there is a predicted energy, and we do the mean squared error loss of the ground truth energy. And we can also, since this is a graph, this is a neural network, we can take some back propagation to calculate the gradient with respect to the input and take it as the force to do some supervised learning on the force. Okay, yeah, and for the improved version of DiamondNet, I think I don't want to introduce the detail, but Yeah, the same motivation as Leni, right? I forgot your name. Hi. No, you are concerned about the angles? Yeah. So previously, the message passing is only conducted by taking the distance as the edge feature, but very obviously, the distance is not enough for describing the energy. So chemically, energy have multiple different components, like not only the the pairwise distance count, also the angle and torsion will make some difference to the energy. So the high-level idea of diamondite is, okay, in addition to distance, I also need to consider some other quantities, and they incorporate angle into the message passing. But I don't want to really dive into the details. You can just think, okay, there is also some angle. I can somehow make them into the edge embedding for message passing. Yes, and the output is still invariant. Because no matter how you rotate and translate, distance and angles all stay the same. We usually call them internal coordinates, so they never change. However, all these kind of methods are relied on like scalarization. So we reduce the coordinates into angles and distance. Is them sufficient description of the geometry? Actually, definitely not. So consider these two molecular structure. So they have an identical distance and identical angle. So when we do that kind of invariant prediction, for invariant prediction is fine. So we can ensure the prediction is invariant. But as you can see, some information is lost in this kind of structure. So these two, our prediction will also be the same. This is wrong. The invariant is a little bit over-invariant. So, but consider if we can truly incorporate some direction or tensor into the framework, like when we add some more description of these two nodes with their like middle direction of their two bonds, they can be distinguished now. So with some tensor feature. So the next large class of geometric GNN is how to incorporate this kind of tensor feature. And I will call it an equivalent graph neural network because this kind of directional tensor will be equivalent with the input coordinates. So it always stores some equivalent feature during message passing. Okay, so another motivation for now why we are not satisfied just with the invariant graph neural network. So we have a class of all the neural network can fully capture all the geometric information, and what we want is the orange part. But now when we constrain our to only invariant features like distance and angles, actually we constrain ourselves to really a subspace, and maybe we couldn't find all the optimal solution. Or in neural network, we usually say we want to define our function as some universal approximation. But here, we constrain our function too much. We want to release some space of our neural network. Okay, so high-level idea of the recent progress of equivalent GNN. It is called PIN. Yeah, kind of interesting. Yeah, this neural network, some part is same, but some part is different. So the same part is we still have like for every edge feature, we will have a matrix, and the matrix control how message is passed through this bound. And the filter or this weight matrix W is still conditioned on just the distance. But what is different is for every node, now we not only have just a regular node embedding as you learned before, as I introduced before, the invariant node embedding. We also, for every node, after every layer, we give them an additional vector feature. The vector feature will change together with the input. So just a quick introduction of what we do for the scalar feature and vector feature. So the scalar feature will be initialized in atom embedding or node embedding. So it is very typical. Input one hot and learn some embedding. And the vector feature, we will begin with 0. So set them all as 0. They are updated with some residual updates. So in every layer, we will learn some updates of both S and V, both the invariant feature and the equivalent feature. And these two features will be used to update it in the ResNet view, ResNet fashion. So just a plus. But whatever. So now we are interested in how in each layer we update the S and the V, the node scalar embedding and the tensor embedding by delta S and delta V. So here is the equation, but I will introduce more details later. So okay, so first I'll see how we update the scalar node embedding. I will see exactly the same as SHNet, so the invariant neural network. So maybe let me still introduce this slide. So yeah, distance input to a matrix as filter, and filter can be used for like phi-s learn some feature of current node of neighborhood node. And the neighborhood node embedding combined with the edge filter W, they combine together as a message in that bound. And for that node, all the messages phi-s multiplied with ws combine together as a message, and the aggregate message. Everything here is invariant because only depends on distance. Still the same. But here we have something different as the vector tensor. So how we update the vector feature? So we input the distance and we have the output weight matrix to control the message passing. And similarly, we also, for all the neighborhood, we use a neural network phi-s to learn some message from that node. However, for the message passing, it is not only two scatter tensor multiplied. After the multiplication, they also multiply with the radius direction. Or the neighborhood to current node direction. So it is multiplied with this tensor. And our tensor embedding will be updated by a weighted sum of all the relative direction. So relative direction from neighborhood to current node. So think about the thing when we do a translation, when we do a rotation of the molecular structure, like from this structure to this structure. The relative direction will change together. So here the relative direction is like this direction, but after you rotate, it will change together. And all the relative direction will change together. So naturally, a weighted sum of all the relative direction will change together. So I call it a rotation equivalent feature. So this is their way to learn the equivalent feature. And what I just introduced is a single layer for updating the invariant node embedding and the equivalent node embedding. And by stacking multiple layers, we can have the output to be still equivalent to the input. So which means when we do a rotation of the structure, the output force will rotate together, and same as what I have introduced before. And also the tensor feature helps to capture more information in our before example to show that distance and angle is not enough. Okay, yeah, this is pain, and yeah, considering the time, maybe skip this summary and begin to introduce the most recent progress of fancy demos of the geometry generative model. Yeah, there are really many exciting progress of protein design or in pharma company. And generative biomedicine is actually the same founder, I think, of Moderna. So they opened another company of AI motivated drug discovery company. So all this kind of task is modern diffusion model. Okay, so today the problem I would like to concentrate. So we need to have a task to concentrate on to introduce our model. So what I do is, given the molecular graph, we want to predict its 3D structure. And yeah, as this friend just say, so every molecule will have different, multiple different structure. So naturally, this is not a prediction task. Prediction task means one-one mapping. But actually, it has multiple stable structure. So naturally, this is a generation task. And physically, there is some distribution of this 3D structure. It's a Boltzmann distribution given some temperature, but never mind. So just want to see there is a distribution.
Why does the molecular graph have to be 2D? Can you have like crossover bonds? Since that the molecular graph G is 2D.
2D.
Why does it have to be 2D?
Why it is not?
Why does it have to be 2D? You can have like crossover bonds.
Crossover bond? What is?
Like the graph on the left, that's 2D. Like if, for example, if you were to draw two bonds that are like overlapping, when you're looking at it from a perspective, that would require a 3D graph. Right?
3D graph. You mean 3D graph?
I mean the one
Oh, you mean define some bond to have the direction, right? So
I mean the bond can overlap, so why does this have to be a 2D atom bond graph? That's what it says on the second line.
This specific graphic is 2D. It doesn't have to be the 2D representation to be a.
oh, I see. Oh, for this task, what we want to do is given 2D, we want to generate a 3D. But yeah, graph can be represented in 3D. That's fine.
When you say 2D graph, you really just mean in a
adjacency matrix.
adjacency matrix.
Yeah.
There we go.
Sorry. Yeah. Yeah. I think yeah. Sorry. I think I still miss some detail. Yeah. Molecule usually have like a 3 level of representation. The most naive way is to actually they have a sequence representation of molecule. Just some atom and some. It is called smiles and yeah. So application on 1D representation is very natural. All the NLP tasks can apply on it. And then graph neural network and everyone work on, I usually call 2D. So it is means adjacency matrix and node feature. And now we concentrate on 3D, but actually it is still graph representation, yes. So every node, we have an additional like coordinates for every node. But the task is 3D generation. That's all what I want to see for this slide. Yeah. Yeah, and similar to the learning, similar to the representation learning for 3D graph, which need to be like capture some invariant and equivariant. Here is the same. So for the generative model, we also want to incorporate some equivariance into the model. And yeah, I know like if I introduce the full information of diffusion model, it will be too time consuming. So I deleted something. But formally, what we are concerned about developing generative model for 3D is generative model essentially want to estimate the likelihood of data and do something like something like maximum likelihood training. And here you can think about likelihood is probability, right? So no matter how you rotate and translate your data or your 3D data, when you input it into a generative model, it will tell you a likelihood. So the likelihood should never change considering the rotation and translation. So this is theoretically the consideration of developing geometric generative model. But here I just, so skip some technical detail of generative model. And some very intuitive understanding of diffusion model. So diffusion model means when we have this kind of image, we will add noise on the image to destroy it to different level. And like in here, our data, we usually denote data as x0. We will have multiple different level of noise to destroy it until random Gaussian. And what we want to learn is, for every time step, we first perturb the data, and it will be a noisy data. And we want our model, we will input xt into our model, and hope our model can predict what is xt minus 1. So how to denoise, similar to here. So we predefine how to perturb or how to diffuse the data. And what we learn is the reverse direction, how to denoise. So diffusion model, the general idea is predefine diffusion process and learn a model to generate by denoising. So this is the high-level idea. And a very brief introduction of diffusion model. There are many fancy mathematics for diffusion model, but here I think I summarized the least requirement of the diffusion model. So you can think about every time we just randomly sample a random noise, or still miss some information. The random noise is sampled from normal distribution. So mean 0 and variance as unit variance. And we destroy the data by to the t-step diffusion data by multiply mu t and plus sigma weighted the noise. And the high-level idea here is in the first step, in the first few steps, by step I mean the t. So when t is very low, we hope that the mu t is nearly 1. So mu 0 is 1. And we hope, we define, And we define sigma 0 as 0. So which means we never destroy the data. And with very low time step t, we just destroy the data a little bit. And what we define for the final step is, I think shouldn't be 1. It shouldn't be capital T. Sorry. So mu capital T is nearly 0, and mu capital T is nearly 1, which means just totally destroy the data into random noise. You multiply a 0 and destroy the data and make it, this is 1, so make it just a random noise. And what we want to do is, every time we give us the data, we perturb the data to some time step, and we put this noisy data and the time step into the neural network, and we hope our neural network learns how to predict the noise vector. And if this can be learned very precisely, you can know here, if we know xt and we know the epsilon, and mu t and sigma t are defined by us, so we always know this kind of parameter, so we can recover the clean data. So this is the high-level idea of diffusion, and this is also the sampling procedure. So we just always sample a very noisy data from Gaussian noise, and we repeatedly from time step capital T to time step capital 0, repeatedly input the model, predict the noise vector, and you subtract the noise vector. You can progressively denoise the data and hopefully recover a very realistic data. So I think most of you have played with like stable diffusion, give some prompt and generate a really fancy image. So really impressive progress of this field. So yeah, this is also from Stanford. So Stephen Ehrman, another professor working on generative model. And yeah, this is some really fancy GIF for diffusion process and the reverse denoising process. They recently formulated this as a stochastic differentiable equation, something like this. Yeah. Yeah, and this is our paper. So we extend the idea of geometric learning of a diffusion model from a typical image to also the geometry. And yeah, very happy it is top 50 most cited paper in 2022. Yeah. So I just want to highlight it's a promising direction and exciting research field. And yeah, this is what we do. So for given a data C0, exactly the same idea. So add noise to destroy it and learn the reverse process to progressively denoising to generate data. However, when you have a look, I want to introduce the work by a very intuitive way. So I just skip all the math in the paper. So when you just have observation of this figure, you will feel like, oh, actually, this is progressively denoising by the noise vector. Actually, this is kind of similar to the molecular simulation. So molecular simulation, when we do molecular simulation, we always have either a classic like a Schrodinger solver or a graph neural network. It will tell you what's the force, and the force will be used to optimize the structure. And here, what you do is you always also have a structure you input to the neural network, and it tells you a denoising direction. So you follow this denoising direction to update your structure. So this is kind of similar, right? Output a dense matrix and optimize your structure. And what's the insight of this observation is similar to force. Maybe we also need to give the neural network the power of capture the equivariance. So how to denoise? The denoising vector should also be equivariant with the input structure. No matter how you rotate your structure, the denoising direction should rotate together. So this gives us the motivation to impose this inductive bias into our model. And what we do is parameterizing the denoising network with equivalent graph neural network. And yeah, and just this kind of thing. This is an visualization from my paper, and it generates, although there is some, like the ring is not on our surface, right? But still fine, still learn something. And it gives the community the first version of how to define diffusion model for geometries. And yeah, I suppose maybe some of you are familiar with diffusion. Considering if you are familiar, maybe you think this is trivial, and I can speak a little bit more. So for diffusion process, as you can look, diffusion process actually is if you couldn't understand, never mind. So it's not important. So diffusion process define a Markov process of generating from prior distribution towards the data distribution. And we have a prior distribution P of CT, and we have all the Markov kernels, and we multiply them together. We can and do some integral of all the hidden latent vector. We can have a probability of the C0. So I just want to see, by diffusion model, we can define a probability of P of data, or likelihood of data, and imposing equivariance into the neural network. Here, the motivation seems like some observation, but the true motivation for my paper is I need to make the likelihood estimation to be invariant to the translation. So no matter how you rotate or translate your structure, diffusion model can be able to calculate some likelihood. And this model can naturally make the likelihood invariant to rotation and translation. So this is some theoretical motivation. And yeah, if you are interested, you can see the paper, but here maybe too heavy to introduce all the math behind this model. Let me click on the figure. This is the most recent exciting progress of diffusion model. So this is now very, very realistic problem now. So we have some protein in our body. So here is also, we have some scaffold protein in our body, and we really want to make it more stable or want to make some antibody to bind it with them or something like this. And these two figures show that we can already use diffusion to generate some, in silicon, generate some promising drug or antibody for some disease. Although there still needs some clinical trial to verify the effectiveness. But yeah, already pretty promising now. Okay, I think, yeah, it's also the time now. So maybe just 1 or 2 minutes to introduce some future direction. Also, what I'm working on recently is if we have a pocket, if we have some ill-behaved protein, how to design small drug for this protein target. And also this is antibody design. So we already know human can generate some antibody for some antigen, and we want to do some mutation, meaningful mutation on the antibody to make it more effective, and we can synthesize it. Okay, yeah, this slide is from many people, and I think the link are also meaningful resources if you want to learn a little bit more. So Jure is mainly for general graph, and Tess is in PhD in physics, I think. And Jian is my previous master advisor. We worked together for the GLD paper, and also Stefano Erman and Yang Song, now a professor at Caltech now. And Ron is, anyway, biology professor, so all kind of resources. And that's all. Sorry for 1 additional minute. Yeah. And thank you.